Hello, everybody. Today, I'm going to share with you some mathematical illusions, seeming proofs that 1 equals 0, or that fractions don't exist, many others like that. But behind the scenes, what's going on with some of the seeming paradoxes that we're going to see has actually caused real difficulty for mathematicians over the years, and sorting it all out has led to some fascinating new mathematical developments. We're going to begin with 3 truly startling proofs, but I'm not going to reveal the tricks of those straight away because it's fun to try and work out what's gone wrong. However, I do promise you that by the end of the lecture, we will have resolved all of the problems and everything's going to be fine. So try and watch out and see where you think my little mathematical sleight of hand is happening. And don't worry if it feels difficult to believe these impossible things. Just follow the advice of the Red Queen. She says to Alice, it's just all about practice. When I was your age, she says, I always did it for half an hour every day. Sometimes I've believed as many as 6 impossible things before breakfast. So, we've all had our breakfast, so this should be much more achievable for us. So we're going to begin with the first 3 impossible things. Let's see. First impossible fact. 1 equals 0. So this might come as a surprise, but, we're going to see a proof. And I'm a mathematician, so, I'm going to be very convincing, I hope. So here's the argument. Why does 1 equal 0? Well, we're just going to consider, think about this innocuous little series of numbers. 1, minus 1, plus 1, minus 1, plus 1, minus 1, and so on. Now, it's pretty obvious what this will all finish with because it all comes in pairs, right? 1 minus 1, another 1 minus another 1. We're just adding but then taking away repeatedly. So this thing is just a bunch of 1 take away 1s. So we're adding a load of zeros together, so we'll end it with 0. Now, there's another way of looking at it, the sort of bird in a hand argument, which is to say we start off with 1, right, that we've got 1. And then what do? We take away 1, but we add it again. We take away 1, but we add it again. Minus 1 plus 1, minus 1 plus 1. So really what we have here is 1 plus a bunch of zeros. So 1. There we go. So we've worked out the same thing 2 different ways, and we've got 0 and we've got 1. So those must be equal. QED, 1 equals 0. So I'm sure you're all happily believing now that 1 equals 0. Just in case you're not entirely convinced, I will give you actually a couple more proofs of this as we go along. As I say, I'm not going to tell you exactly why this doesn't work right now, but we might suspect something murky is going on with these ... dots. That they hide a lot of problems. So we'll come back and think more about infinite series later on. But let's have our second impossible fact. The smallest positive number is 1. Now, this is actually very good pedagogically, right? Because teachers tell us, research has shown, that one of the major stumbling blocks for youngsters learning mathematics, and some of them never get beyond it, is fractions. So once we've proved the smallest positive number is 1, there'll be no need for fractions anymore, and everyone can be happy. So let's prove that the smallest positive number is 1. So currently we don't know what it is, right? So let's investigate it a bit. So here comes the proof. So we don't know what this smallest positive number is. Let's call it x for the moment. Obviously, x is at most 1, because 1 is a positive number, and x is the smallest one. So x is certainly less than or equal to 1. OK, but x is a positive number. If you take the square of a positive number, you still have a positive number, right? So x squared is also a positive number. X is the smallest positive number, so x squared can't be any smaller than x. So that tells us that x is less than or equal to x squared. OK, now, x less than or equal to x squared. X is positive, it's not 0, so we can divide through by x without, I'm not dividing by 0 or anything weird. This is OK. I can divide that little equation through by x on both sides, and I get 1 is less than or equal to x. And now we've got a number sandwich. Best kind of sandwich. Because we've showed that 1 is less than or equal to x, but x is also less than or equal to 1. So x is trapped. It has to equal 1. So we've shown that the smallest positive number is in fact 1, which is great. No more fractions. Maths has become suddenly a lot easier. So again, have a think. What do you think has gone wrong there? We'll come back to that later. Final of these three impossible factors coming up. And I thought, as I'm the Gresham Professor of Geometry, we should do some geometry. So we're going to do some geometry around congruent triangles. I'll show you, before then, a couple of warnings, because I don't want to, lead you astray. Here, we just have to say ahead of this, watch out. St. Augustine does tell us to beware of mathematicians and all those who make empty prophecies. But, okay, well, I don't know, say what you like. St. Augustine, be honest with us. Goethe, on the other hand, I don't know if this is more insulting to mathematicians or to Frenchmen, but he says whatever you say to either of them, they translate it into their own language, and forthwith it means something entirely different. So those are the warnings, but now let's proceed and see what we can see about triangles. Okay, so there's the basic setup. I've got any old triangle, ABC, right? Take a triangle, your favorite triangle. Now, what I've drawn in two lines. We're going to have some more lines. I thought I'd do it step by step. So we've bisected that angle A. So bisecting an angle is something we've probably all learned to do at school with a ruler and compass. You can do that construction. So bisect the angle A, and that line is coming down, and then we're going to cut the opposite side in half, so the perpendicular bisector of that side. So we've cut it into two halves, the midpoint is at D, and then we've got that perpendicular coming up, and they're meeting at O, and we're going to add some lines from O. We're going to add in, we're just going to join O to the other two sides, O to B, O to C. I'm not claiming those angles are being bisected or anything, we're just joining those lines. And we're going to drop perpendiculars to the remaining sides. Again, I'm not claiming that that chops those sides in half, but we can still drop those perpendiculars. Okay, that's a bit of a complicated setup. So now watch me like a hawk, because I'm going to do some things with congruent triangles, and you've got to see where I may or may not be lying to you. Okay, so I'm going to take them in pairs. We've divided this triangle into 6 little smaller triangles. Let's look at the 2 blue ones at the bottom, that pair. So I claim they're congruent. How do I know? Well, we've got a common side, OD, and BD and CD are equal because what we got OD there is the bisector, right? So BD equals CD, so those two sides are equal. And between them, we've got the same angle, happens to be a right angle. So one of the rules for congruent triangles is side angle side, okay? So by that rule, these 2 blue triangles are congruent to each other. All right, next pair of triangles, the red ones. What have we got here? The angles at A are equal by construction. We made the angle bisector. At P and at Q, we've got right angles. So we've got 2 matching angles, and then, of course, the third angles must be the same. So all the angles are the same in these triangles. So they're definitely similar triangles, but also they have a common side, AO. So that makes them congruent. Okay, so it's another pair of congruent triangles. And now finally think about the 2 yellow triangles there, the ones that are left. And so these ones, what can we say about them? So they're right-angled triangles. At P and at Q got right angle. The hypotenuses of those are the same, OB equals OC, because the blue triangles are congruent. And we've got another pair of matching sides, PO and QO are equal because the red triangles are congruent. So right angle side side, another of the criteria for being congruent, the yellow triangles are congruent. So we've now got these 3 pairs of congruent triangles. So what can we say from this? Well, think about the side AB. Now, because the red triangles are congruent, AP is equal to AQ. And because the yellow triangles are congruent, PB is equal to QC. So AP equals AQ, PB equals QC. Now you might see where we're going. AB is AP plus PB, but AP equals AQ, and PB equals QC. So we've got the AB is equal to, in length, AQ plus QC, which is just AC. So what we've shown is that AB equals AC. So it's an isosceles triangle. But this was any old triangle. So we have proved the amazing theorem that all triangles are isosceles. Fantastic. So if you are puzzled by that, good. We'll come back and think more about it later. Okay, well, by this point, you might be starting to ask yourself many things about your life choices that led you to this room today, but you might say, well, okay, what actually then is a proof? Because these proofs perhaps seem to prove something that isn't true, and that's not really what we want in a proof. So what is a proof? I mean, the idea of proof goes back thousands of years. It's one of the things that makes mathematics mathematics. So we can sort of loosely say that what are we doing when we prove something? Well, it's a sequence of logical deductions starting from some things that we all believe are true. You know, we might call them axioms, some initial assumptions. Then there's a sequence of logical deductions, everything following from what's gone before, that establishes the truth of a given statement. So we start with 3 impossible facts, 3 proofs, and we've had 2 quotes. So now we need to have 1 terrible joke, because that has to be the ratio. There's another meaning of the word proof, 0.5% of alcohol. And occasionally, combining those things can make things go terribly wrong. So here's the advice for today. Don't drink and drive. There we go. Yeah, thank you. Yeah, I know. I thought, I've only got 1 more lecture after this as Gresham Professor, and I don't think I've told that joke yet. So, it had to happen. Anyway, let's carry on and think about the first definition of proof, not involving any percent of alcohol at all, if you're doing it properly, where we make deductions following on from our initial assumptions, and we go through the proof. So there's a direction of travel. We start here, everything follows from what's gone before. Now, getting that the wrong way round is something that can cause big issues. And I'll give you an example. And this is a mistake that is a really common pitfall, in fact. So you might get asked to show that some 2 algebraic expressions are equal to each other. It's very tempting to make that the first line of your proof and say, right, let's start here and then mess around with the algebra and multiply things out and cancel things and do some stuff, and then we end up with 0 equals 0. Well, that's true. Great, so the original thing was true. Now, this is very dangerous. It's a dangerous thing. In this case, I mean, the original statement does happen to be true, but deducing something true is possible even starting from something false. So you've got to make sure your direction of travel is in the right direction. Because if you don't do that, you risk proving things like this. So here, I'm proving that 1 equals minus 1. So I start with 1 equals minus 1, and then I square both sides. 1 squared will equal minus 1 squared. Well, then on the left you get 1, on the right you get 1. So 1 equals 1. Well, I know that's true, so the original thing must have been true. Now, of course, that's nonsense. We can see that it's nonsense because I've proved something false here. But it doesn't look like nonsense necessarily in the thing above, because it just so happened that what we're aiming to do it happens to be a true statement. But in mathematics, we don't only want to be able to trust proofs of things we already know are true. Rather, destroys the purpose of this. So it's so important to make sure that our proofs are going from beginning assumptions to the end, and not the other way around. Okay, let's have our 4th impossible fact. And it's a good one. It's going to help all of our financial calculations here. 1 penny equals 1 pound. Okay, here's the proof. It's a very nice short proof. So 1 penny, well, what is that in pounds? That's 0.01. Okay, now 0.01 is 0.1 squared. So we just make that change. Okay, so now I've got 0.1 squared. But 0.1 pounds, put that back again, that's 10p. Yes, 10 pence. But now, of course, we've got to square it now. So 10 squared is 100, and 100 pence is 1 pound. Hooray! So I'm pretty sure this is how the Bank of England does quantitative easing. So it's at least as good as any other explanation I've heard. But okay, what's going on here is there's something up with the units. Something's going wrong when we're trying to change between pennies and pounds. And actually, problems with units have caused real-world issues on many, many occasions. I wanted to just mention my top 3 of these, because it does matter. I mean, we can see that this is wrong, but sometimes there are issues that arise when people don't notice problems with units. So the first of these, probably the most famous, the Mars Climate Orbiter, which, very unfortunately, that mission failed at a cost of, something like $120 million, because some bits of the collection of companies and people who were doing this, some people were expecting to receive some numbers that are needed to calculate various thrust in the craft wanted to receive the numbers and were thinking they were receiving the numbers in newtons of thrust, and they were actually being sent the numbers in pounds of thrust. And those two do not give you the same answer. So unfortunately, because of that mess up between metric and imperial, the mission sadly failed. We can go back. This is not a new phenomenon, so it's not all the fault of metric. This is a much older example. So this is the Swedish warship Vasa, which sank mere moments after launch in 1628. And then they raised it in the 1980s, and they had a look at what might have gone wrong. And what they found, or one of the problems was, they found on the ship, it literally just been launched. So there were still a few bits and bobs of the construction materials, and they found some rulers. They found 4 rulers. And they were able to sort of deduce that there seemed to have been 2 teams of carpenters or shipbuilders working on this ship, one on the port side, one on the starboard side. And on one side, the rulers were measuring Swedish feet, and on the other side, they were measuring Amsterdam feet. And one of those is about 28 centimeters, and the other one is about 29 centimeters. And that discrepancy was enough to make the weight of the ship unbalanced, like one half, the things were thicker than others, and so it was unbalanced and catastrophe. So even if you're both using feet, you need to make sure you're both using the same feet. Now, the final example is a slightly different one. So this is the High Rhine Bridge. It was built to connect the Swiss city of Laufenburg to the German city of Laufenburg. So both have the same name, but they're on different sides of the Rhine. One's in Germany, one's in Switzerland. Okay, so this was a problem because in Switzerland, the altitude is measured from a base point which is related to essentially a big rock in Lake Geneva. And on the German side, altitude, sort of mean altitude is measured based on a measurement that's sort of mean water level somewhere in Amsterdam. Okay? Those are different from each other. Now, they knew this. They did know this. They're complete idiots. The difference is about 27 centimeters. So they said, okay, well, we just have to take account of this in our calculations. And at this point, my heart goes out to them, because I, too, often miss out minus signs and then have to go back and find them again. Right? Rogue minus signs are the banes of many people's lives, including mine. A minus sign went wrong. And so instead of getting rid of the 27 centimeter discrepancy, they doubled it. And when the halves of the bridge were kind of coming together and closer to meet, they found they were 54 centimeters apart from each other, and sort of emergency changes had to be made. So in that case, it was, we're using the same measurements, but we're starting from different levels, and the rogue minus sign messed everything up, which they seem often to do. So if we think back to, units mattering, if we think back to our impossible proof that 1 penny equals 1 pound, it's easier to spot what's gone wrong, if you hadn't already, if we were to try and do this same thing but with centimeters and meters. Because we straight away can see that some of the things that we're saying are equal to each other aren't even measuring the same thing. Because we've got meters, 0.01 meters, and we're claiming that that is equal to some number of meters squared. But meters are a unit of length, and meters squared are a unit of area. So there's no way those can be the same thing. It's harder to spot that with pounds and pennies because we don't often think about square roots of a pound or a square of a penny. So what went wrong here was that we just sort of glibly put these units inside squares and square roots and didn't pay attention to what was happening. So yes, units, important, and that is a warning to us all. Okay, so let's think now again about 1 equals 0. Just in case you didn't believe me, I'm going to give you 2 more proofs that 1 equals 0, because I really want you to believe it by the end of today. And they're increasing in mathematical sophistication, so we just used ones and minus ones before. Now we're going to bring exponents into it. So just a couple of observations. We all know the laws of powers. Yeah? Anything to the power 0 is 1. Right? So x to the 0 is 1 for any value of x. But on the other hand, if we take 0 and raise it to any power, you just get 0. Multiply some zeros together, still 0. So 0 raised to the power y equals 0 for any y. So I simply set x and y both to be 0, And you'll see that from the first expression, I've got that 0 to 0 is 1, and from the second one, it clearly equals 0. So it clearly is equal to both 1 and 0, which are therefore equal to each other. So 1 equals 0. Okay, marvelous. Easy. Just in case you're still not convinced, I'm going to bring calculus into it, okay, because calculus can do anything. So this is the only glimpse of calculus in this talk, but it's a good one. So this isn't calculus yet, but look, I'm just showing you here what we mean by something squared, which we all know. So 2 squared is 2 plus 2, 2 lots of 2. 3 squared is 3 plus 3 plus 3. 4 squared would be 4 lots of 4. So in general, for any number x, x squared is just x plus x plus x plus x, like x times. Okay, so now, here comes the calculus. Just differentiate on both sides. If you remember your calculus, don't worry if you don't, you can just use one of the other proofs that 1 equals 0, and you won't lose anything. Differentiate on both sides. And we all know when we differentiate x, with respect to x, when we differentiate x, we get 1. So a bunch of 1s on the left-hand side. And when we differentiate x squared, you may remember, the answer is 2x. So now on the left, we've got x lots of 1, and on the right, we've got 2x. So for any value of x, we just have x equals 2x. So I'm going to substitute x equals 1, and that gives you 1 equals 2, and then you just subtract 1 from both sides. 1 equals 0. So listen, I've given you 3 proofs. I think it would frankly be churlish if you didn't now believe that 1 equals 0. So let's assume you do believe that 1 equals 0. That allows us to do something very interesting. We can now prove that everything is true. Everything. It's a corollary. This is a theorem that's a consequence of a previous theorem. So here's the corollary. Let S be any statement, then S is true. So this solves all of our worries, and we can prove everything. So here, let's do that. So take any false statement, whatever you like, any false statement at all, F. Now, if I happen to know, if I've managed to prove that this thing, that at least one of F and S is true, if I know that that statement is true, then the thing that's true must be S, because F is false, right? So if I can prove that at least one of S and F is true, then we will be able to deduce that S is true. Okay, all right. Now, let's consider a particular false statement, 1 equals 0. So that's a false statement, I think we probably agree. But we also now have to agree, because I proved it 3 different ways, that 1 equals 0 is also true. We just proved it 3 times. So this happens to be also true. So F is true. In that case, it's definitely true to say that at least one of S and F is true, because F is true. Marvelous, but we just said earlier, and nobody told me I couldn't, that if we can prove that statement, that at least one of S and F is true, then S must be true. So you have to now agree that S is true. Okay, QED, every statement is true. So this is how high the stakes are, right? If we let even one false statement into mathematics, then it just renders everything, all bets are off, everything is true. So we've got to be really, really careful and try not to prove anything that's false. I try to do that in my mathematical life. Okay, so with that in mind, we've already proved everything is true, so, maybe we could stop there. But let's carry on, because I want to show you 6 impossible facts, because I admire the Red Queen so much, we try and practice these things every day. Okay, so impossible fact number 5. It turns out that 0 is a positive number. Didn't know that before. Now we do. 0 is greater than 0. Okay, so let's prove that. Okay, we're going to think about these 2 theories. So x is going to be 1 plus a third plus a fifth plus a seventh plus a ninth. So kind of the odd, 1 over the odd numbers added together. And y is going to be 1 over the even numbers added together. A half plus a quarter plus a sixth plus an eighth, and so on. So there are those 2 things. We don't know what those are, but let's just call them x and y. All right. What happens if we double y? So now we've got just double each term, so 1 plus a half plus a third plus a quarter, and so on. So this is actually the combination of x and y, because we've got 1 over all of the odd numbers and interleaved with 1 over all the even numbers. So 2y is actually equal to x plus y. So if we solve that, well, not solve it, but if we rearrange, just take away 2y from both sides, we get x minus y equals 0. Okay, so that's all good. But there's a slightly different way we can think about it. Here's the different way. So now if you think about x minus y and just, x and y, x is above y here, so we can just do like compare the terms or take away the terms pairwise. So we can have 1 minus a half, and a third minus a quarter, and a fifth minus a sixth, ... That's also x minus y. Now the reason I put that bracketing there is because if you look at each bracket, within each bracket, you've got something that's strictly greater than 0. 1 minus a half is bigger than 0. A third minus a quarter is bigger than 0, right? A fifth is bigger than a sixth. A seventh is bigger than an eighth, and so on and so on. So we're adding together infinitely many things that are each bigger than 0. So if we add together infinitely many positive numbers, we're going to end up with something bigger than 0, for sure. So x minus y then is bigger than 0. But hang on a minute, we just saw above that it equals 0. So again, we've got this fantastic result that 0 is bigger than 0. So that's that proof. All very nice. So I think it's now time. We already saw an infinite sum doing something a little bit suspicious, let's say, right at the beginning. Here we've got another bit of something odd going on with infinite sums. So it's now time, I think, to talk about the challenge of infinite series. How can we understand what's going on? Have we really proved that 0 is greater than 0? I hope not. I hope we haven't proved that 1 equals 0. So what do we do with infinite series? And the problem, one of the problems is, if we think about this one, so 1 plus 2 plus 4 plus 8 plus ... powers of 2. We can see that that's getting bigger and bigger and bigger. It feels like intuitively like the sum of that ought to be infinity. Okay, we're adding more and more and bigger numbers. We could plausibly say that equals infinity. Well, okay, that's our x. If we work out 1 plus 2x, that's 1 plus twice everything in there, so 1 plus 2 plus 4 plus 8 plus so on. And if you multiply all those things by 2, it becomes 2, 4, 8, 16, so on. So actually 1 plus 2x is just x again. So now we've got 1 plus 2x equals x. And if you solve that, you get x equals minus 1. So am I saying that infinity equals minus 1? I mean, computer scientists say that, don't they? Maybe that's true. But it feels like that isn't quite right. So what could we do? Which bit of this reasoning is something that we should disallow? So we could say, well, let's say we're not allowed to do calculations with infinity, for example. That would get us out of it. Just say this is banned because it leads us to weird paradoxical ideas. You could do that. But that wouldn't help you with the first example we saw. It wouldn't help you with this 1 minus 1 issue, because there, nothing's zooming off to infinity. We did it one way and got 0, we did it another way and got 1, but there's no infinities in there, in the calculation. So that feels like we could banish infinity, but that doesn't fully fix the problem. So maybe it's something else that we need to do. You could say, well, I'm just not going to allow adding up infinitely many numbers. That's clearly problematic, and I'm just going to ban it. This doesn't sound very intellectually curious, so we don't want to do that. But also, we can't really afford to do that, because we do need these things. Not these ones precisely, but we need infinite series. We use them all the time. If we want to work out, it's kind of useful to be able to know and think that 3/10ths plus 3/100ths plus 3,000ths plus 3/10,000ths plus ... What is that? The decimal 0.333, 0.3 recurring. That's the decimal expansion of 1/3. It's kind of useful to have that. Or you might say, okay, well, we won't do that. We'll just have fractions. We'll just write a third. We've got something right there. But of course, that will not work for numbers like pi, which are irrational. There is no fraction that exactly is pi. So we need these ... We need to somehow incorporate them into mathematics in a way that it puts us on a firm footing where we don't accidentally prove that 0 equals 1, which takes the shine off your afternoon if you accidentally prove that, or maybe it makes it more fun. So we need to be able to work with infinite series. And therefore, we have to work out how to avoid these apparent paradoxes. So how do we do this? Well, let's think about an example. So if I took a half plus a quarter plus an eighth plus a 16th, so 1 over the powers of 2, add those together, plus dot, dot, dot. What we do with this or other series is we say, well, obviously we can't actually add infinitely many numbers together. So we make better and better approximations. And what we do is to work out the sum to a given point. We'll call that partial sum. We work out these partial sums, so the sum to 1 term, the sum to 2 terms, 3 terms, and so on. So if we do this, I've actually plotted the first few of these on a graph just to show you what happens. So the first term is just a half. If we add a quarter, the sum is 3 quarters. A half plus a quarter plus an eighth is 7 eighths. Then we get 15 sixteenths, and so on and so on and so on. And you can see I've done, so this is the graph of the partial sums that we're working out. And you can see it looks really rather like we're getting closer and closer and closer to 1. And in fact, if you can work out an expression for what is the nth partial sum, the sum to n terms, and it's 1 minus 1 over 2 to the n. So as n gets bigger, that 1 over 2 to the n is getting smaller and smaller and smaller. We really are getting closer and closer and closer and staying close to 1. So, I mean, we could give a formal, very formal definition of what we want to say, but the basic idea is we would say that this series does have a limit. The limit is 1, and it converges to 1. And the way we prove that is that we show that however tiny a number you pick as a distance away from 1, at some point, eventually those partial sums will become and stay as close as you like to the limit that we think it is. So here we think the limit is 1, and you can prove that however tiny a number you give me, I can guarantee that there will be a point beyond which all of those sums stay closer to 1 than your teeny number. And so that's informally, I've defined the concept of convergence there, that this series converges to this limit, which in this case is 1. So that's the basic idea, and we can see that this does now help us with our 1 minus 1 problem. What about this? Well, if we work out those partial sums, first one is 1, and then it's 0, and then it's 1 again, and then it's 0 again. It just keeps flip-flopping between 0 and 1. It's never going to converge because it never settles down to being very, very close to a single number. It just keeps flip-flopping between. After an even number of terms, it's 0, and after an odd number of terms, it's 1. So this thing does not converge with this definition we're working with. So if it doesn't converge, what's the opposite of that? It diverges. This is a divergent series, even though it doesn't zoom off to infinity, but it never settles on one value. So it's meaningless to say it equals 0 or it equals 1. It never doesn't equal anything because it never sits still. All right, so we can think, well, when would things, how do we know if something does converge? I mean, that's clearly quite important. So certainly, if we're adding up all these things and we've got to stay within a smaller and smaller distance from what we think is the limit, the things that we're adding on are going to have to get smaller and smaller themselves. So if we think about something like this is called the harmonic series. So we're adding 1 plus a half plus a third plus a quarter plus a fifth plus dot, 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 dot. If you look at the partial sums here, and I've plotted the first about 100 of them, you can see that it kind of 1, and then 1.5, 3 over 2, and then you add a third. So the bits you're adding on get less and less each time. Kind of the gradient of this thing is settling down. It hasn't settled down to anything yet, but it sort of looks as if maybe it might, given enough time, it's getting flatter and flatter, the line. So it might settle down to something. But it doesn't. And let me explain why it doesn't. So if we think about this series, we can group the terms. So we've got 1, and then a half, and then we're going to group the next 2 terms, a third and a quarter, then the next 4 terms, up to 1/8, then the next 8 terms, the next 16, and so on and so on. And the reason we're doing this is because inside each bracket, everything before the last term is strictly greater than that. So 1/3 is bigger than a quarter. 1/5, 1/6, 1/7, those are all bigger than 1/8. So whatever this sum is, it's bigger than what I've just written here, where we've replaced a third with a quarter. We've replaced everything in that bracket by 1/8, and so on. And 4 lots of 1/8 is a half, 2 lots of a quarter is a half. All of the brackets add up to a half now. So we know whatever this sum is, it's bigger than 1 plus a half plus a half plus a half forever. And that's clearly going to be bigger than any number you like to mention. If you want this to be bigger than 1,000,000, you just do 2,000,000 of these brackets and you're bigger than that. So even though it slows down, it grows slower and slower, this series gets to be, if you wait long enough, bigger than any number. So this cannot converge. This is also a divergent series. So it's not enough to just have the terms getting smaller and smaller. We need more than that. So you do have to be quite careful. There is a tweak we can make to this series. If we alternate pluses and minuses, you get what we call the alternating, for obvious reasons, harmonic series. So this is 1 minus a half plus a third minus a quarter plus a fifth minus a sixth, and so on. Now, again, I've plotted some partial sums here, and I've gone up to the 200th partial sum. And you can see, this isn't proving anything, but it's looking quite good for converging, because it's sort of oscillating around and then settling down to a number that seems to be somewhere just slightly less than 0.7. And you can actually prove properly that if you work this out, this does converge. We'll call it S. It converges to the logarithm of 2, log 2, which is about 0.69, something like that. So this does converge. It's a convergent series. But there's an issue. Mathematicians discovered this. So they're looking at this, and they said, yes, it converges to log 2, fine. But let's think about calculating that in a slightly different way. Is there a different way of calculating this thing? So we're going to add all the same things up, but just in a slightly different order. We know we can do this if we're adding 2 or 3 numbers. It doesn't matter which one we add first. So seems okay. So what have I done? I want to explain, or I want you to be convinced that we have got all of the numbers in there, all of the terms in there. So each of these brackets has 3 terms. The first term that I'm highlighting in green is 1 over the odd numbers. So we got in the original ordering, it's 1 minus a half plus a third minus a quarter plus a fifth. So we're adding all the 1 over odds, and you can see that they appear at the beginning of each of these brackets. So you've got 1 plus a third plus a fifth plus a seventh, and so on. And then the other 2 terms are the 1 over even numbers, just in the original order, but we're putting them in pairs. So minus a half minus a quarter in the first bracket, minus a sixth minus an eighth, minus a tenth minus a 12th, and so on. So we have got everybody. Now let's think about these brackets then. The first 2 terms in each bracket, 1 minus a half is just a half. What have we got? We've got a third minus a sixth, that's a sixth. A fifth minus a tenth is a tenth, and so on. So we can simplify a bit. This is still the same sum. And now we've got this calculation to do. You'll notice that all the denominators now are even. So we can bring out a factor of a half. And then we'll see we've got a half of 1 minus a half plus a third minus a quarter plus a fifth minus a sixth. That sounds familiar. That's our original sequence, or our original series. So we just seem to have shown that S is equal to half of S. But if S is a number, that sort of implies that S is 0, which, have we just proved that the logarithm of 2 is 0? We hope we haven't. that would be bad. And this was a genuine issue that mathematicians realized, oh my goodness, we worked out this thing, and then somehow now it also seems to be equal to 0. What is going on? Because, as I've said, if you're doing 1 plus 2 plus 3, you can rearrange that. You can do it as 3 plus 2 plus 1 or 3 plus 1 plus 2. You get the same answer. So why can't we do this now? Well, sometimes you seem to be able to get away with it. Sometimes you don't. What's going on? And what is going on was finally worked out by the great mathematician Bernard Riemann in what is now known as the Riemann series theorem. So this is going to solve all our problems. Well, perhaps just the ones about infinite series, not like all our problems. But it's a great theorem. I need to give you one bit of terminology, and it's this. If you've got a series, like the ones we've seen, there's this concept of being absolutely convergent. And that's not like really convergent. You can either be convergent or not. But absolutely convergent is indicating taking the absolute values of the terms of the series. So the absolute value of a number is just like its magnitude, ignoring the sign. So the absolute value of minus 7 is 7, for instance. So we say that a series is absolutely convergent if the series where you add the absolute values, the moduli of the numbers, is convergent in the way we've talked about with limits. So as an example, that alternating harmonic series we saw, that's convergent to log 2, possibly, but it's not absolutely convergent, because if you turn those minus signs into plus signs, you retrieve the harmonic series that we saw was divergent and went off to infinity. So that's the definition we need, and now here comes the theorem. It says if a series is convergent, but not absolutely convergent, like our alternating harmonic series, this is really amazing. It can be rearranged to converge to any limit at all, or even to not converge, to diverge. So we saw a rearrangement of the alternating harmonic series. We started off, it converged to log 2, then we rearranged it, and it seemed to end up being 0. Actually, you can rearrange it to sum to anything at all, to converge to any limit at all, which is pretty amazing. Now, does this mean that this log 2 thing is wrong? No, what it means is that when you rearrange it, you get a different answer. So if you've got this kind of series that converges but isn't absolutely convergent, you cannot rearrange the terms. Because if you do, any arguments you make become null and void. You have changed the sequence of partial sums by rearranging. So you're just not allowed to do that. If you don't do that, then you're OK, and you can trust the answer that you get at the end. By contrast, these absolutely convergent series are brilliant, because for them, you can rearrange it as much as you like, and it will not affect the answer. So they're like the gold standard of series. That's what you want. You want something to be absolutely convergent, then you can do whatever you like to it. So this really resolved everything, and it means we can avoid these scary apparent paradoxes and accidentally proving that 0 equals 1. So this deals with the kind of infinite series sort of problem. I want to give you one more impossible fact, and then I know that I owe you a couple more explanations from the beginning. So this one, we're going to prove that half equals a third. Now, seems unlikely. This proof is based on one that was devised by a French mathematician, Joseph Bertrand, who wanted to illustrate some difficulties with probability. So think about this question. So you take a circle, and you have to find the probability P that a random chord of that circle, so just a line drawn between 2 points on the circumference, that any random chord is longer than the side of the inscribed equilateral triangle. Okay? What's the probability that a random chord will be longer than the side of that triangle? So I'm going to show you how we can work this out. So take your random chord. How do you do that? Well, you pick 2 random points on the circumference, right? So pick your first point, and then you pick another point, and that gives you a chord. Okay, so to think about whether this is going to be longer than the side of the triangle, I'm going to just rotate the triangle. It doesn't matter if I rotate that picture on the right to make it fit in with whatever I need to do. So I'm going to do that so that one vertex of the triangle coincides with the first point of my chord. And then we can see it's quite easy, because the chord's going to be longer than the side of that triangle precisely if the other end of it, the second point that we chose, lies in this arc, which is between the 2 other triangle vertices. And that's a third of the circumference. So there's a 1 in 3 chance of that happening. So clearly the probability is 1/3 of this thing happening. Okay, great. Now I'm going to give you a different argument. So the different argument goes like this. We can define a chord in a slightly different way, or choose our chords in a different way. Because if you take a chord of a circle, if you bisect it, taking perpendicular bisecting, you might remember, that line will go through the center of the circle. So you can define a random chord in a slightly different way. You can pick a random radius and pick a random point along that radius and draw a perpendicular at that point. That will give you a chord. And so every chord is uniquely determined by picking a radius and a point along the radius. Okay, so what's the criterion then? How do we know if that chord is longer than the side of the inscribed triangle? Well, again, I can put my inscribed triangle wherever I like. It doesn't change the size. So I'm going to put it so that its base is at right angles to this radius I've got. And then we can see that the chord will be longer than that side precisely when the point that I choose is inside that triangle, so above wherever the triangle meets the radius. So where does the triangle meet the radius? Well, we can quickly do a bit of trigonometry. If we join a little radius there, we can see what we've created there is a right-angled triangle, which has a 30-degree angle, and sine of 30 is a half. And so the height of that little triangle is half the radius. So the triangle meets this radius halfway along. Any point, when we're making the chord, if we draw the point in the first half of the radius, it'll be longer than the side of the triangle, otherwise not. So clearly the probability is a half. And I'm convinced by both those arguments. And there are other arguments that we can see as well. Neither of them is wrong. Neither of them is right. The problem here is that we haven't defined the problem correctly. And this is a real issue in probability. If you've got an infinite amount of things to choose from and you're trying to select randomly, you have to be very, very careful because the way you are making your choices often will affect the answer. So we have two perfectly valid bits of reasoning. If we choose our chord by picking two random points on circumference, the probability is 1/3. If we choose our chord by this other way of radii and point on a radius, the probability is a half. We've got to define how we're choosing those random things from this infinite collection. And this is one of the, a major step in understanding probability theory. That actually sometimes we don't have enough information and it doesn't make sense to define a thing. And this deals as well with that one of the proofs that 1 = 0 I gave, where I said that 0 to the 0 is 1 and 0 to the 0 is 0. Now both of those kind of make sense. They're reasonable things to say. It doesn't mean that 1 = 0, because actually if you don't say how we are going to define 0 to the power 0, then you can't trust the answers you get. So normally, in fact, what we say is 0 to the 0 is undefined. We just don't define it because we want it to fit in with something to the x is 1. X to the 0 is 1, but we'd also like to fit in with 0 to the anything is 0, and you can't make both of those happen. So we just say, we're not going to define that, there be dragons. And sometimes you have to do that. That's the only thing that makes sense. Okay, so we've got a few errors to clear up in the last few minutes. We talked about whether the smallest number really is 1. I'm sorry to have to say it isn't. It isn't, but what went wrong? Well, what went wrong is, really what we've got here is a proof that there is no smallest positive number. It's a proof by contradiction, a reductio ad absurdum, because we started with an assumption that there was a smallest number, and it led us to something ridiculous. It didn't actually prove the smallest positive number is 1. So we could rephrase this as an actual theorem. There is no smallest positive number. And the proof is, we say, well, let's imagine there were, and do a thought experiment. So let's assume let's assume that there is a smallest positive number, and we'll call it x. And then we did our little deduction and showed that x would have to be 1. But that's clearly ridiculous because, a half is a positive number that is smaller than 1. So we ended up in the realm of something false, a contradiction, and so our assumption that there is a smallest positive number must have been wrong because it led us to this false statement, this contradiction. So proofs by contradiction are really wonderful things in mathematics. Some of the best proofs there are involve this technique. You just take an idea for a walk, and if it fails, once you've eliminated the impossible, whatever remains has to be the truth. So I didn't want this next thing. I want to show you another proof by contradiction. I didn't want to say it's an impossible fact because I fully believe its conclusion. All positive integers are interesting. So let's call this the optimist theorem. So let's prove this. Let's imagine a ridiculous thing to imagine. Let's imagine that's not true. Then there's at least one boring positive integer. So if there's at least one of these, we can look at the whole set of them and look at the smallest one. We'll call that n. So n is the smallest of all the positive integers. N is the very smallest, first, boring positive integer. That's pretty interesting. Pretty interesting fact about n. So n is interesting, which contradicts what we said. So they're clearly, as we all know, there's no boring numbers at all. They're all interesting. That's cast iron proof. Okay, so there's one proof left that we haven't dealt with, and that was the amazing fact that all triangles are isosceles. And here, well, let's begin at the beginning. That diagram I drew, here's an isosceles triangle, and we're going to see what happens when we move the top, so ABC. We're going to see what happens when we move that top vertex A so that it stops being isosceles. The red line you see, that is bisecting the side BC, so that's going to stay fixed. But the angle bisector, which is currently hiding behind the red line, because when it's an isosceles triangle, those two lines are the same, the angle bisector is going to move, and we're going to look at where they intersect, where the angle bisector intersects this perpendicular bisector. So we'll just watch this happen, and you'll see that that place where they meet isn't actually inside the triangle. Now, you can see it gets close, oh no, it's not going to make it. It's not inside the triangle. Now, that on its own isn't necessarily an issue, because maybe all the calculations or whatever we did didn't rely on the diagram necessarily, but, well, we'll see. So the diagram ought to look a bit more like the thing on the right, not the thing on the left. However, all of those calculations or deductions about the congruent triangles, they are all still completely valid. Those were correct. All of those pairs of triangles really are congruent to each other. So we still, genuinely it's true that AP equals AQ and PB equals QC, but the problem is, guess what? It's a rogue minus sign. I knew that there'd be one somewhere. So yes, AB, if you look at the diagram on the right, AB does equal AP plus PB, and AP does equal AQ, and PB does equal CQ, but that does not equal AC, because Q is outside of the triangle now. We had to extend that line to drop a perpendicular. And so AC does not equal AQ plus QC, it equals AQ minus QC. And that, of course, changes everything. So here, the diagram, it wasn't that it was wrong, but that it led us to think something that was not guaranteed to be correct. So if you see some geometry, just make sure to draw a diagram that's perhaps quite accurate and see what you get. Well, let's finish up with another theorem. There exists a triangle with 3 right angles. Now, we've proved all triangles are isosceles. This should be a doddle. Well, now this is kind of the final thing that I want us to think about, that when we prove something, we start with initial assumptions. When we prove that the angles in a triangle add up to 180 degrees, you may remember this proof. It relies on the parallel postulate, because you have your triangle, and the top point of that, you draw a line through that top vertex parallel to the opposite side. And then you do some stuff, and you get very quickly the angles add up to 180. If you do not have the parallel postulate, then you can't prove, at least not in that way, that the angles in a triangle add up to 180 degrees. That particular proof doesn't work. And it turns out that there are geometries, for example, the one we have on the surface of a sphere, in which the angles in a triangle do not add up to 180 degrees. And here is one that has 3 right angles. And that exploring the idea, the question, when is this true? When could this be true? Is actually one of those most powerful questions in mathematics. So it's really fun to explore, when might this thing be true? Now, this is obviously a very, non-Euclidean geometry is a very deep and exciting and interesting area of mathematics. I thought I'd give you a slightly less highfalutin puzzle to finish with, along the line of what I call fake proofs of true facts. So fractions, again, sadly they exist. We all know how to cancel fractions, right? If there's the same thing on the top and the bottom, we can cancel it. So 16 over 64 does equal 1/4, because we just cancel those 6s. Yeah, that's how cancellation, isn't that? No, okay, we'll do another one. Okay, 19 over 95, right? Cancel the 9s. Yes, so it works. Does not always work. But when does it work? Right? It's quite fun. In fact, you can extend this. If you have a 1 and a bunch of 9s, and then the same number of 9s on the bottom, and then a 5, you can cancel all of those pairs of 9s, and you do magically get the answer 1/5. There's a little proof of that underneath. Very quick thing. It's actually a true proof for once. So you take n 9s and then a 5, that's 10 to the power n plus 1. Take away 5, bring out the factor of 5, then you get 2 times 10 to the n, so 2 with n zeros minus 1, and then that equals exactly 5 lots of 1 and then n 9s. Okay, so you can actually prove this. So the challenge is, find other true facts with fake proofs like this. And in particular, I don't know what the answer to this is. Is it ever true that you can add fractions in the way that some 8-year-olds and 9-year-olds would like to add fractions, which is a over b plus c over d equals a plus c over b plus d? So that's a little challenge to keep you going until my next lecture, which is my very final Gresham lecture next time. on June the 4th, we're going to talk about some real proofs and the beautiful ideas that we can exploit and enjoy in mathematics. And I'm going to show you some of my favorite proofs. But we'll stop there. Thank you very much.
Thank you, Sarah. I'm Martin Elliott. I'm the Provost of the College, and it's always an immense treat for me to hear Sarah speak. I'm also very reassured that I now know how the Chancellor works out the next budget. It's tremendously powerful. I'm going to take some questions online first. Is there anything other than an infinite series that can cause false statements to be proven true?
Well, yes, proven. There's got to be a hole in your proof somewhere. But, yes, and as we've seen some of the ways that can happen. I did not divide by 0 at any point today. But that's another way that you can often make false things happen to be true. You disguise it. You do some algebraic calculation. You say, let x equal y at the beginning, and then you wait a few lines until everyone's forgotten, and then you divide by x minus y, and hope nobody notices. So there's a lot of ones that involve division by 0, but I thought, this is a very superior audience, and they are going to spot division by 0 just straight away, so I didn't do that.
Let's take some questions from the floor before I go back to those online. Does anybody have one? Yes, sir.
The one I hadn't seen before, and I'm not quite sure of the problem, the differentiation one, the x plus x equals x squared. Can you explain that one, please?
So I think, this is where you have x lots of x, and then on the right-hand side you have x squared. Now, one problem is that I had x lots of x, and when I differentiated all those little x's, I got 1s, but I didn't do anything about the fact that I had x of them. And I think that's the basic issue. So I ended up with x lots of 1, but it's not really clear how you make a function that says here are x lots of x, and actually you sort of force yourself to write x squared, and that's the issue. So, if you were to try and do this from first principles and properly represent the left-hand side, I ignored the fact that I had x lots of this thing, and I didn't do anything about that. That's really what's gone wrong there.
Any more questions on the floor? Otherwise, I'll read you one out. Why are there irrational numbers that can't be expressed as a ratio of two other whole numbers? And does it show us anything or prove anything?
Why are there, you might have to ask a higher power than me, but there definitely are. There are, and so you can see this, if you take just a square whose sides are 1, and the diagonal of that square cannot be expressed as a fraction, however hard you try, square root of 2. And these are called irrational numbers, and they are everywhere, but nothing to be afraid of. It's just that our human minds who thought of using fractions to write things just didn't realize that there are these other numbers out there. So, yeah, they vastly outnumber, in fact, the numbers that can be written as fractions. Almost every number that you pick up random off the street is irrational.
How frequently do these things happen with the conversion of pure maths, as it were, into applied maths? Apart from the first example you showed of us landing on Mars, how frequently do disasters happen when people get these sequence of assumptions wrong? So
I think we're quite lucky in that most of the time, I would say, we've got away with things over the years, let's say. So in the kind of 200, 300 years ago, people would kind of play around with infinite series and assume everything would be fine. And because the series they were playing around with happened to be quite well behaved, mostly you can get away with it. But that's no way to do mathematics. But it took a while to really come up against these issues for real. And I think one risk that can happen if you're transferring kind of from pure mathematics to applied mathematics is maybe the pure mathematicians have this cast iron thing that says, under these conditions and these conditions alone, you're allowed to do this. And then perhaps that may slightly get lost sometimes, and then you just sort of, I know I can do that, and I'm sure it's fine. Just every so often, it isn't fine. But in the real world, of course, you have mathematical models, you have approximations, and you can test it, everything, and make sure that it will work in real life. But it is important to make sure, that we're not going to end up with with proving impossible facts. So occasionally it crops up.
Next question from the floor. Okay, I've got one here. I don't know. Oh, it was the one at the back there. Sorry, didn't catch your eye.
Thanks for that. Is there a governing body or anything to accept a proof?
Ah, well, okay, yeah, there should be. Well, what in practice, what happens is when you're a mathematician, you think you've got a theorem, you will write that up as an academic paper, you will send it to a journal, and the journals then will send that out to referees. So people, other mathematicians who will look independently at what you've written and try and follow your argument, and if there's something that they don't understand or why is that allowed, then they send it back and say, can you explain how you got from here to here? And if you can't, maybe you realize there's a mistake. So the idea is, peer review will capture any errors that you might have made, and as you go on in your mathematical career, hopefully you make fewer gross logical mistakes. It still can happen, and perhaps not these kind of things, but maybe other things. And of course, everyone can make mistakes accidentally. So yeah, it's peer review that happens, and then things are published, and your other fellow mathematicians will read them. So that's the closest we get, I guess.
So, just hang on for the mic if you don't mind.
I'd like to say the last thing you said there, a great example of that was Andrew Wiles' proof.
Yes, so Andrew Wiles, so famously the proof of Fermat's last theorem, which came some years after Fermat claimed he'd got a nice little thing that didn't fit in the margin. But Andrew Wiles proved Fermat's last theorem, but his first proof, as submitted, had a fatal flaw. And happily, that was able to be fixed. But the first original proof, when was that, like 93, had this mistake in it that it wasn't like, oh, you've forgotten to do some trivial thing. It was genuinely a fatal flaw in the proof. But happily, he did manage to correct that. It took a lot of work, and then the correct version was submitted, and everyone does now believe it.
So I've got one last question which borders on the philosophical.
Oh.
The basis of mathematics is the concept of zero, unity, and infinity. Do those concepts apply universally?
Well, if you accept, certainly those are very important concepts, 0, 1, and infinity. And you can almost, so I remember James Joyce, famous mathematician, he had a little notebook, and he wrote these sort of links between these three concepts. So 0 divided by 1 is 0, 1 divided by 0 is infinity, and infinity divided by 1 is, so all of these things, you can sort of relate to each other. So they're wonderful concepts, and in a way they're all linked to each other. But I think that they are universal because, and not 0, i.e. you don't have anything, that's clearly a thing that can happen anywhere. 1, the basic unit from which everything else is built. I feel, that's got to, if you have any alien civilization and they count, they're going to start at 1 like we do. These things are not really choices. And there's God, what's the name of that mathematician who said that God invented the natural numbers and everything else comes from man, right? But yeah, I think these things are universal concepts.
Thank you. Well, I'm sure you'll agree with me that Sarah is more than 1 in a million, 1 in infinity. Thank you very much indeed.